Alright, so today we're going industrial and we're going to start talking about Internet of Threats. Apologies, Internet of Things. Honest mistake. So Internet of Things has grown a lot lately. It started with home devices like home automation and cameras and baby monitors and things that, alert you when there's an open door, an open window, control the heating and air conditioning. But we start seeing them nowadays in businesses all over the place, in business applications as well, like monitoring production lines, flooding or earthquake warning systems, smart cities, smart parking, smart agriculture. There's just so much Internet of Things happening nowadays. Now, unfortunately, as smart as they are trying to sound, most of these devices are not built with security in mind. They were not designed to be secured out of the box. And actually, the easier they are to use, the more vulnerable they can be. Okay, so Internet of Threat devices, Internet of Things devices, honest mistake again, IoT devices frequently show up as hacked in the news. We hear about attacks and vulnerabilities and exploits regarding IoT devices so often in the news. It usually happens by finding out how easy it is to get unauthorized access or even to install some botnets to run on these devices. And this happens for a number of reasons. First of all, because they have very limited hardware and very limited operating systems, but they're still an operating system. Most likely they're all based on some version of Android or some tuned down version of Linux. So many of the classic vulnerabilities which apply to Android or Linux apply to those IoT devices as well. Due to the limited hardware, sometimes the security features are eliminated completely or are implemented in a very, very unsafe manner. And also, they're not designed with security in mind because, let's face the truth, most of the people who buy them are not IT people. They're not really concerned about security in the first place. They are concerned with usability and with the gimmicks, all the smart and nice features that those smart objects offer them. So they don't even know that there is a risk in there, and sometimes they don't even care. And when the customer doesn't care, why should the company care, right? On top of this, oftentimes they don't even have admin interfaces or accessible interfaces to configure anything on them. Let's say you find out that a certain type of request sent over the wireless network can crash your robot vacuum cleaner. Can you do anything about it? Can you install a packet filter, an access list, a firewall on a smart vacuum cleaner? No, you cannot. And just to give you some insight as to how dangerous these IoT exploits can actually be, here's an article about a casino's internal network, including all the gambling applications, how the internal network was hacked through the smart thermometers installed in their aquariums. So it's that bad. And the vast majority of these IoT devices are based or are running something called an embedded operating system. And by definition, an embedded OS is some type of a system or an operating system designed for a device which is supposed to do a single thing. It's designed to execute a single function. That can be as simple as something like a heart rate monitor, or as complex as a computer for controlling a self-driving car. Or an assembly line inside of a factory. They're usually static, which means that they cannot be changed by the user, only by the manufacturer. Again, this comes back to the problem of detecting a vulnerability and not being able to do anything about it. And sometimes the updates available are very limited or not available at all, and sometimes they cannot be updated at all because they might have non-standard service ports that require some manufacturer's software and tools. For example, at some point I tried to update a smart speaker in my home. It's the type of speaker that connects to the Wi-Fi, connects to smart home assistants, and does a lot of stuff. And I just thought it might be a good idea to update the software from time to time. It had a USB port in the back, so I just visited the vendor's website, and the manual said that I'm not allowed to perform any kind of software updates because that special USB port actually has to be connected to a non-standard voltage, which is atypical for a USB port, in order to be able to interact with it and to provide the software update as a service upgrade. So unless I contacted the manufacturer or an authorized support partner, I was left out in the open without any kind of updates. and I still am. Now, some embedded systems that are based on PLCs, those are programmable logic controllers, can be reprogrammed, can be updated, but you will need the vendor's code to do so. A high-risk type of embedded systems are found in POS systems or kiosks, and they can be compromised to steal customer data or customer credit card data if they allow credit card payments, or change data in some commercial application. And of course, they are high risk because they are extremely exposed to the public. Another category of devices are the so-called system on a chip, basically an embedded system on a single chip, right? Obviously. The purpose is to have a very small computer that saves space and power requirements. It has its own CPU, its own memory, its own connectivity ports to talk to the outside world, storage, everything that makes it work like a computer, but at a much lower scale. One example of this is Arduino, for example, widely used in IoT devices, or Raspberry Pi, which is not so much as an IoT device anymore as a full-blown computer, but still falls under the category of system on a chip. I mean, I was able to stream a 4K video from a Raspberry Pi, so that's not just an IoT device anymore. That's a computer, and even a general purpose one. Real-time operating systems are another type of embedded operating system. They have very limited functions and extremely time-dependent execution. Their focus is on time functions and on executing operations on a specific point in time. This means that they have to be more reliable, more stable than general computers. Often these restrictions mean that they have absolutely no security features because they're used on assembly lines, controlling safety functions, machinery in constructions, or even, elevators, medical equipment. So any attack on these would consist in damage, and they can be attacked just like any other device. The difference is that in most cases you only have to delay that functions, the functions in the RTOS. You don't even need to crash it or to make it do something more complex. On a chip or a car assembly line, a denial of service of 1 second delay could be devastating. And there's no security. Most of the time, there's no security simply because there are no spare CPU cycles to treat any detected attack. There's no way for the CPU to pause its current execution and then start handling some sort of a security function, right? Because it has to process at every single point in time a specific instruction. It is not allowed to do anything else, which is exactly what makes it so vulnerable. Here's an example of an attack or an exploit that happened on a real-time operating system, which is VxWorks from Wind River. And this real-time operating system powers car electronics, factory robots, controllers, aircraft and spacecraft, wireless routers, medical equipment, digital display, whatnot, right, and plenty of other stuff. So really dangerous if any kind of vulnerabilities are found in these real-time operating systems. Finally, another one are FPGAs, Field Programmable Gate Arrays. As the name says, they are reprogrammable chips that are designed for repetitive, relatively simple functions and can only execute operations from a predefined, pre-programmed set. Now, we also have non-programmable chips, so those that are hard-coded from the factory that you cannot change, and those are called ASICs. Application-specific integrated circuits. Now, both FPGAs and ASICs can be used for functions such as packet encryption, packet decryption in firewalls, in IPSs and IDSs in proxies, or packet switching in, switches. Now, FPGAs are vulnerable not to just physical access, but also to supply chain attacks. Remember, we talked about those. If some devices are intercepted in transit or in the factory where they are built, malware or backdoors can be installed in those reprogrammable FPGAs. Here's one example called Starbleed. And unfortunately, as you can see right here, since the bug is in hardware, it cannot be patched with software, and the only fundamental solution is to replace the chips. So it's that bad. Next up, we have to talk about building automation systems, or BASs. They are sometimes similar in behavior to smart home systems, but they're applied to enterprise. And so they're more complex, right, to an enterprise building. Basically, it's about the physical access controls and the badges and the RFID tags, biometrics and the lights and the temperatures in the conference room, air conditioning, fire suppression, video monitoring on the hallway, all in one or more large digital systems that are networked for monitoring and control. Now, in one perspective, BASs are somewhat similar to ICSs as well, to industrial control systems, since they also rely on embedded controllers and sensors with a central monitoring control interface. You do have a console from which you control the lighting and the temperature in a room, but you also have sensors all over the place that feed back information about those changes. Now, unfortunately, most of these systems are often overlooked as not being part of the actual network from a security perspective. Now, some are installed and maintained by third parties, so they're ignored whenever a security assessment is conducted. Some use proprietary protocols like BACnet or DINET or something like that, which are not centered on security, and those PLC can be exploited through these networks. On top of these, most of these solutions are administered centrally from some type of a web application, from a web interface, which is designed to be used only internally. So they're not properly secured. The code is designed to work in an isolated and controlled environment, so often there is no encryption. Everything is in clear text and sent in clear text and stored in clear text, or even worse, hard-coded within the application code itself, like security credentials hard-coded in the application or stored right next to its code. Now, a subset of these building automation systems can be a PAC, which is a physical access control system, which is a network dedicated for door locks, window locks, surveillance, and so on. To read more about security in building automation systems, I would direct you to have a look over this paper right here, and also over this article about discovering and defending against vulnerabilities in building automation systems. Now, you're going to get both links in the video description, so I would highly advise you to at least glance over them. Another very important and widespread category of embedded systems are vehicles and drones, like cars and drones. Have a lot of intelligent electronics built into them. And we're not just talking about the entertainment system in your car, but electronic engine control, stability, fuel consumption, even driving assistance or parking assistant or self-driving. Each such system is an ECU, which is called an electronic control unit, controlled by CANs, controller area networks, which are just serial buses. The interface to this system is usually called the OBD or the OBD2 onboard diagnostic module. You might have used it if you ever installed some GPS tracking device in your car or someone else's. Now, that CAN bus, that CAN bus that we mentioned, is very similar to the Ethernet shared networks. There's no security at all. All ECUs on the bus receive the same messages, so there is only broadcast and there is no source addressing or any kind of authentication, just like the Ethernet from the old times. Now, of course, access to the OBD port can basically crash a car, since denial of servicing the CAN bus can make all this electronic control cease to function. But these days, we also have remote ways to access the CAN bus through cellular connections, like you get the ability to start your car from your phone, or heat up the seats in your car before you get into the car. Some cars also create mobile Wi-Fi hotspots, which also opens another gateway to potential attacks. Like this example, which you might have heard about, how to kill a Jeep's engine on the highway without even being inside of the car. And coming back for a second to the industrial zone, industrial control systems are responsible for automating control machinery, on assembly lines, for example, and critical infrastructure, like, the systems that provide water, power, health services, communications, even nuclear facilities. In either case, they are regarded in a special way because the systems that they control can become very dangerous if we lose that control that we have over them, and can pose high risk to human lives. Now, just to clear the terminology here, an ICS within a single site is called a DCS, a distributed control system. I know it's it's awkward, it's counterintuitive, but in a single site, it's called a distributed control system. Now, these systems run some software on normal computers on PLCs, right? PLCs that gather data from outside sensors and controllers, which are called field devices. Now, these PLCs are linked by either a field bus serial network or by Ethernet to actuators that operate the actual engines, like the valves and circuit breakers and so on, including sensors that monitor things like position, temperature, and other parameters. There's also a component called the HMI, that's the human-machine interface, and as the name says, that's the interface that a human uses to configure and monitor the output of a PLC. Another one that you might have heard about is SCADA, which stands for Supervisory Control and Data Acquisition. Not very intuitive, but as you probably know, a SCADA industrial system controls large-scale ICSs with multiple sites. Now, it is often deployed on a completely separate network because SCADA systems can run on general-purpose computers, and due to the strict requirements, updates are very rare or even impossible to apply, which is why some companies completely air-gap the SCADA network or isolate it with firewalls. And unfortunately, most of them are running some legacy software on legacy hardware for which there are absolutely no more security patches or updates available anymore. So from a security perspective, what you should do for a SCADA system is to first document and monitor all the links and the connections or the possible connections to your SCADA system. Also, use any built-in security system if you have any available. Keep in mind that some of these systems only work on legacy PC operating systems, so try to stay away from those. But if you don't have a choice, think about air gapping the network, and air gapping is a very important concept for the CompTIA CySA Plus exam as well. Now, sometimes these systems are managed through web applications, which can also be vulnerable to a whole lot of threats. The actual web application attacks from top 10 OWASP, for example. Also, don't forget about physical security, not just physical access to those systems or to those computers, but things like, ways to communicate with the outside, like through USB drives or CD-ROM drives, because they're most likely gonna have some CD readers in there. And finally, don't forget to audit periodically and hire good technicians who understand security. And there are some dedicated security systems for these problematic industrial systems out there, especially data diodes, which are purposely built to only allow traffic in one single direction. That is, they don't even have internal circuitry necessary to allow traffic to flow back from the outside or from the internet. So there are special devices designed that way, kind of like a hardware firewall that filters traffic at a physical level. And just to give you a couple of examples of dedicated security solutions for SCADA systems, one of them is the Cisco CyberVision, and another one that we just mentioned are the data diodes for true segmentation of those problematic network segments. Finally, the last one you should know about is Modbus. This is a protocol used in ICS to read and update configurations on PLCs. It's very, very old, with no security in mind. Again, was designed originally for a field bus serial network, not even Ethernet, but it has evolved nowadays to use Ethernet and TCP/IP. And since you don't really have to dig too much on the internet to find some proof of vulnerabilities that apply to the Modbus protocol, here's an example. That's an academic paper about this. And here's another one. Again, an academic paper about the vulnerabilities of the Modbus protocol. Now, fortunately, things aren't exactly that bad, so there have been some improvements to Modbus, especially the introduction of TLS in Modbus. So even though most of these are considered to be legacy devices, there comes a point where legacy means dangerous, so don't go there, right? Be aware that things can be improved in industrial systems as well. So here's an article about some good news about the security improvements that can be performed on top of the Modbus protocol. And here's an article with some bad news, a piece of malware that targets energy sector systems and even includes references to the COVID-19 pandemic. And last but not least, if you don't know about Stuxnet already, please read this article. You'll find all the links in the video description. You need to know about this. You need to know what happened here, and you need to understand the disastrous effects a simple USB stick can have on a SCADA system. Alright, that's it. Now, all this story about IoT devices, industrial systems, real-time operating system, embedded operating systems, and so on is really complicated, and the CySA Plus exam tries to touch these subjects just a bit so that you can become aware of the security risks that can happen on each of these tightly controlled systems. Now, you really don't have to go so much in depth to understand how these things work, but you do have to understand the security principles and the security, let's say, red flags that we talked about over the course of this video. Alright, so understand how security is implemented in these very restrictive systems, and you should be okay for the exam. Alright, so thank you so much for watching. See you next time when we're going to be talking about log analysis and continuous security monitoring. Hope you liked it. Like and subscribe, and see you next time.